Today, we want to continue our path of finding the derivative of a function. Our algebraic style of the day is going to be radical functions. And then we are also going to look at the connection between the graph of a function and the graph of the derivative of the function. Yesterday, we looked at the graph of the function and figured out what the graph of the derivative should look like. Today, we want to do that backwards. We want to look at the graph of a derivative and figure out what the function should look like. All right. Let's start with our algebraic style of the day. Now, this is where we are using the definition of the derivative to find a derivative. This is an excessive use of algebra for what is a very short process once we get to chapter 3 and start learning our shortcuts for derivatives. But this is making us better at algebra. So it's good algebra training and exercise. All right. Today, we want to put radical functions into the definition of the derivative and then do some algebra stuff to cancel out the h in the denominator. The algebra stuff that we need when we're dealing with radical functions is rationalize. We need to be able to rationalize. Usually we rationalize denominators. We were told when we learned about radicals that we can't have radicals in the denominator. That's in an age of calculators, that's really just not true. But it does get us into rationalizing, so that's usually our first introduction. But when we're dealing with radical functions, our strategy, the algebraic trick that we need is we just need to rationalize. So the big idea is that if I have a square root of a minus the square root of b, and I multiply this by the square root of a plus the square root of b, this will equal a minus b. That gets rid of the radicals. And that's going to be our technique for dealing with radicals. This is as far as we'll probably need to take it. It would be really weird if I started to ask you to rationalize cubics because we haven't done that before. Although that's a fun bonus surprise question. So let's start off with f of x is the square root of x, the simplest radical function I could think of. And we still want to find f prime of x. I know some of you know some math secrets. And so you already know what the derivative should be. You're looking at the square root of x, and you're saying that f of x is an x to the 1/2 power. So you already know that f prime of x should be a 1/2 x to the minus 1/2. So you already know what's coming. Some of you said find f prime of x when we have the square root of x. I'll just put square root of x into Wolfram alpha, and one of the things it will tell me is the derivative of the function I put in. So if you haven't heard of Wolfram alpha, you need to have heard of Wolfram alpha. I shockingly did not have it queued up. And I also spelled it wrong. So if you haven't heard of Wolfram alpha, you need to have heard of Wolfram alpha. So there it is. But let's work on our algebra skills by finding the derivative of the square root of x by rationalizing. So let's begin. We're going to plug f of x. So f of x is the square root of x. And so f of x plus h, that's going to have to go into the definition of the derivative, will look like the square root of x plus h. Now let's plug these parts into the definition of the derivative, and we'll see that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's just the definition of the derivative. I need to plug in the function that I'm working with, which is the square root of x. So this is going to be the limit as h goes to 0 of the square root of x plus h minus f of x, which is just the square root of x, all over h. Like we saw yesterday, when we just had to simplify the polynomial or rational functions, our goal is still the same. We want to cancel out the h in the denominator. We want to cancel out this h from the denominator so that we can just let h go to 0 and evaluate the limit that way by plugging in 0. Can't plug in 0 yet because there's still h in the denominator. That's what we need to cancel. Here's how we're going to do it. The numerator has a square root of x plus h minus a square root of x. That's what we're going to rationalize. Normally, we rationalize denominators. Here, we're going to rationalize the numerator. So I'm going to multiply by the square root of x plus h plus the square root of x. Since I can't just multiply by whatever I want, I will multiply by 1. One of the great tricks of mathematics. When you're stuck, multiply by 1, add 0, or change your variables. The reason that this works is that when I multiply the square root of x plus h minus x times the square root of x plus h plus x, I end up with the square root of x minus h squared minus the square root of x squared. I'm just looking at the factorization of the difference of squares. But since all the terms are square roots, I'm going to cancel out the square roots. So this is going to end up being the limit as h goes to 0. In the numerator, I'm just going to have an x plus h minus x. In the denominator, I'll have this h, and I'll still have x plus 8, the square root, of x plus h plus the square root of x. So that's just following the multiplication. Multiply these two terms by the other two terms, so just FOIL. Square root of x plus h times the square root of x plus h is the x plus h. Square root of x plus h plus the square times the square root of x is a positive version of the next term, which is negative square root of x times square root of x plus h, and then minus and minus is minus. Root x times root x is x. So by rationalizing the numerator in this case, the x's cancel out. And after the x's cancel out, I'll be able to cancel an h out of the numerator and the denominator. So now that the x's will add up to 0, I'll have the limit as h goes to 0. The denominator will be h times the square root of x plus h plus the square root of x. And the numerator is just h. And now what we wanted to happen happens. H divided by h is equal to 1. Now we can let h go to 0 by just plugging in 0. Now when h goes to 0, I get 1 over the square root of x plus another square root of x. So I just get 1 over 2 square root of x. So when we're dealing with radical functions and we want to find the derivative of a function, we just rationalize. Gets rid of our radicals and allows us to cancel out the h. Any questions?
Yes, Professor. How do you get the denominator to square root of x? I forgot.
So down here, I have when h goes to 0, this term becomes the square root of x. And this term is still the square root of x. So now I have just one square root of x plus another square root of x. So that's 2 square roots of x.
Oh, I remember now. Thanks, Professor Litch. Got it.
Any other questions? Note that if I write the 1 over the square root of x with an exponent, that's just x to the negative 1/2. So it still matches up with what we got from those of you with your secret math knowledge that we haven't got to yet. It still works out. Taking this one step further, this rationalization process works because we had square roots. The idea of rationalizing still holds if we have something other than square roots. But if, for example, our function was, say, g of x equals the cube root of x, now our rationalization, the difference of squares, is no longer going to be useful because I don't care about squares, I care about cubes. So here, rationalizing with the difference of squares is not going to help. We're going to need to rationalize with the sum or difference of cubes. So the big deal in this problem is that rationalizing with the difference of squares is not going to help. Try to rationalize with the difference of squares is not going to help because we're going to need cubes to get rid of a radical with an index of 3, a 1/3 power. We're going to need the difference of cubes to rationalize this. So the difference of cubes says a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So if you multiply all this out, you'll get, if you multiply a minus b times a squared plus ab plus b squared, you'll end up with a cubed minus b cubed. So this is going to be important because if the a and the b have 1/3 powers, they're cube roots, I need to cube the cube roots, but I can't have any cube roots left over. If I just multiply and cube root of x minus 1 times the cube root of x plus 1, I'll have the cube root of x squared minus 1. That doesn't help me. I've still got radicals. Just to match this up with the previous problem, g of x plus h is going to be the cube roots of x plus h. So our definition of the derivative, g prime of x, will still be the limits as h goes to 0 of g of x plus h minus g of x over h And now we have to figure out what the rationalization is going to be. Now we need to figure out what A and B are and put those to rationalize the cubes. You can see by my writing of question marks and the dot, dot, dot at the end of the, after the equal sign, you can probably figure out this is the question that I am not going to be answering today. So how would we use the definition of the derivative to find the derivative of the cube root of x? Because it's requiring some more specialized knowledge. Now, for those of you in the know, or for us in the future, if you ask your future self how to do this, your future self would say, look at the g of x as x to the 1/3 power, and then just multiply by the exponent, then subtract 1 from the exponent. So your future technique will just be using that. But if you want to challenge, use the definition of the derivative. Not because using the definition of the derivative is an important thing that you're going to be doing in your future career as a fill in the blank, but it's good algebra training. Any questions? All right. What we would want to do, the other thing that we would want to do is look at combinations of radical and rational functions. I started off with the most basic radical function I could think of, square root of x. But it could be that we have a radical function that also has some rational elements to it. But the big idea is that we just do algebra until we can cancel out that h. So for example, if we had a function, say p of x is 1 over the square root of 1 minus x squared, this has denominators and radicals in it. This one has denominators and radicals in it. So we might have to do a combination of techniques. I would need to write down what p of x plus h looks like. So I'm just going to replace x with x plus h. So my difference quotient will have p of x plus h minus p of x all over h. Our goal is to still cancel out the h. We have denominators. We know how to fix that by getting a common denominator. We also have radicals. We know how to fix that by rationalizing. So in p prime of x, we would have the limit as h goes to 0 of 1 over the square root of 1 minus the square of x plus h, the square of the sum of x and h, minus p of x, which is 1 over the square roots of the difference between 1 and x, and the square of x, all over h. The goal is to still cancel out the h. We get common denominators to deal with the rational parts. We use rationalization to get rid of the radical parts. Rationalization So rationalize to clear the radicals. Common denominator so that we'll be able to divide by h. We'll just use a combination of our previous techniques to deal with this slightly more complicated function. You can tell by the fact that I wrote instructions over here, and that now I'm following that up with just ... that we've come across the second problem that second question that I'm not going to answer, but leave as a challenge to the reader. Any questions?
Specialist, is there any ways can you give us the answer? Do you have it?
I have the answer, but I'm not going to give you the answer until you do work for the answer. So I'm not going to give the answer to this one right away because we'll just copy it down and we won't learn anything. You have to struggle with this one before I'll give you the answer. If you have algebra, if you have future techniques, we can view P of X as 1 minus x squared to the negative 1/2. And so P prime of X, we can write as a negative 1/2 times 1 minus x squared to the negative 3/2. And then but we need to multiply by a negative 2x because of the chain rule. So if we know future is future style. In the future, that's how we'll find the derivative of this function. But right now, we need to work on our algebra skills. We need to look at this and see where we can rationalize that, and know that we have to rationalize to clear radicals and get a common denominator so that we can cancel out the h. Our goal is to still cancel this h so that I can evaluate the limit by plugging in h equals 0. That's our goal. With that goal in mind, we need to list the tools that we have at our disposal, and then we need to practice using those tools. Questions? You've got to practice using your tools so that you could use them properly. Even when the tool usage seems really simple, like everybody knows how a screwdriver is supposed to work, but you can definitely be bad at using a screwdriver, and you can definitely be good at using a screwdriver. And I'm not just talking about power drills. Like dealing with the screwdriver when the screws are made out of, I don't know, I think they make them out of aluminum. And you got to realize that this screw is only going in one time and it is too soft for your application. You can either sit there and regret it, or you can learn techniques for dealing with soft screws that are never going to come out again. All right. The other thing that we want to talk about today is how we can look at the graph of the derivative of a function and figure out what the function looks like. So now we want to do what we did yesterday, but backwards. We want to look at the graph of the derivative. And see what that tells us about the graph of the function. Recall yesterday, we did this the other way around. We looked at the graph of the function and we figured out what that told us about the graph of the derivative. the big idea is that when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. When the derivative is zero, the function is flat. So if the derivative is positive, then the function is increasing. If the derivative is zero, then the function is flat. And if the derivative is negative, then the function is decreasing. Someone's getting deliveries. Dog's got to watch out. Make sure that guy doesn't deliver us a murder. See? All right. So when the derivative is positive, the function is increasing. When the derivative is zero, the function is flat. When the derivative is negative, the function is decreasing. This goes both ways. Yesterday, we looked at this the other way. We looked for where the function was increasing and decided that the derivative must be positive on those intervals. We looked for where the function was flat and decided that the derivative was zero at those points. We looked for where the function was decreasing and decided that the derivative was negative on those intervals. So let's play this game backwards. We're going to draw a picture of the derivative, and we're going to use it to figure out what the function looks like. So here's going to be a picture of the derivative. So here we're looking at a derivative. I'm going to mark these points where the derivative is equal to zero. I'm going to call this first one, let's say that that's x1. And the second point is going to be x2. So let's look at what's going on with the derivative and figure out what's going on with the function. Let's say down below, I'm going to have another x-axis. And I'm just going to line this underneath. So x1 is going to be here, and x2 will be directly underneath x2 on the graph of the derivative. So all right. This is a separate graph. We're looking at two graphs. Let's see what we can see. For x before x1, the derivative is negative, so our function needs to be decreasing. So for x less than x1, f prime of x is negative. We're looking at the derivative. The derivative in this chart, the derivative is it's the sign of the derivative that we care about. So f prime of x is negative. So f of x is decreasing. So whatever we draw down here, we're going to draw something that's decreasing. When x is equal to x1, so at x1, f prime of x1 is equal to 0. So at, or let's say when, that's what I was doing yesterday. When x equals x1, we see that f prime of x1 is equal to 0. So f of x is flat when x equals x1. So wherever I draw the function f, when I get to x1, I need to draw it flat. It needs to flatten out. It needs to go from decreasing to flat. And then between x1 and x2, for x, between x1 and x2, f prime is positive. So f of x is increasing. So between x1 and x2, whatever I draw down here for f of x, it needs to be increasing. So we can see a lot already. Before x1, we draw something decreasing. At x1, it needs to flatten out. And then between x1 and x2, it needs to increase. When we get to x2, f prime of x is back to 0. So I'm going to draw, before x1, I'm going to draw a decreasing function. At x1, I'm going to draw a flat. Between x1 and x2, I'm going to draw an increasing function. At x2, it's going to be flat again. And then after x2, f prime of x is still positive, goes back to being positive. And so f of x is increasing again. So at x2, the graph of f flattens out, but then continues to increase. So I'm going to draw down here a function f of x that decreases up to down to, as we go to x1, goes flat at x1, increases from x1 to x2, flattens out at x2, and then starts increasing again. So that means f at x1 is going to have to be lower. I'm going to draw it flat way down here. Flat. I'm going to mark these little flat places. So I'm not sure where it hits these values, but I know that it's going to be low down there and up high up there. Because between x1 and x2, the graph needs to be increasing. Then I just make a graph that decreases down to x1, is flat down here, so it looks like it's turning around. I need to increase and flatten out at this point, but then increase after that point. So I'm just going to have this little flat area. So here's my graph decreasing to x1, flat at x1, increasing after x1, flat at x2, but increasing after x2. So here's my sketch of f of x. We just looked at the connection between when a function is increasing, the derivative is positive. The sign of the derivative tells us about the direction of the function. The sign of the derivative indicates the direction of the function. The sign of the derivative is telling us about the direction of the function. Any questions?
Yes, for Freshelich.
Yes.
On the f prime of x function,
Uh-huh.
so if x is less than x1 is the negative, then the f of x function you have to drop below the x axis. Is that what it means?
No. It just means when f prime of x is negative. So f prime is below the x-axis. The values of f prime are negative, so that means the function f of x is decreasing.
Mhm.
We have no idea where f of x is relative to the x-axis. Because here's another function that fits this same description. Decreasing down to x1, flat at x1, increasing from x1 to x2.
Oh, it could be like that too, right?
Yep.
It doesn't have to be below the x-axis. Okay, I got it. Thanks.
We could also draw a version of f of x that is down below the x-axis, but not forever. These ends go to infinity.
All right, thanks.
In this direction, we lose some information. We see that we lose some information when we look at the derivative. Any questions? Comments? Deep thoughts? All right, so the connections that we want to make right now is that the sign of the derivative tells us about the direction of the function. Derivative increasing, derivative positive, function increasing. That's the main thing that we want to get. The sign of the derivative tells us about the direction of the function. We want to make sure this is solid. We want to practice this graphing business because we're going to add another layer to it. We're going to start looking at the second derivative, which is just the derivative of the derivative. So we're going to have the function, the first derivative, and the second derivative. We're going to be adding another layer on top of this graphing information, because the second derivative tells us stuff about the first derivative and also stuff about the function. We just want to make sure we get this first direction of the sign of the derivative tells us about the direction of the function. Any questions? Comments? Snide remarks. All right. Your job this week is to practice your algebra skills by using the definition of the derivative to find the derivative of a function. Also, you're working on homework. There are 3 homework assignments this week from chapter 1, so section 1.4, 5, and 6. And there are 4 sections from chapter 2, so section 3, 4, 5, and 6. These are ostensibly due on Sunday, but as usual, you can work on them after the due date. That's just a suggestion. That's where I want you to be. That is keeping up with what's going on in the class. I have also got a quiz on continuity that I need to make a few edits on to make sure it works, because I'm trying a new thing. And then, so that will show up, and that will be something that you're working on this week. Any other questions? Comments? Deep thoughts? All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.